Hello Math 2 students. In this video we're going to rationalize an expression when the denominator is a binomial. And so to do this we will eliminate the radical by using the conjugate. And so before we start doing an example problem, here's a binomial 3 plus root 5 and here's its conjugate 3 minus root 5. Here's a binomial, root 7 plus root 2. Here's its conjugate, root 7 minus root 2. So the binomials look the same, except this is a sum and this is a difference. And as you'll see, the sum and difference pattern that we've learned before plays a large part in how the conjugate works to eliminate the radical from the denominator of an expression. In our first example, you can see that we have 8 over 1 plus root 3, and this radical expression is not in its simplest form because there's a square root in the denominator. So to eliminate that square root, we're going to rationalize. But because the denominator is a binomial, we're going to rationalize it in a different way. We're going to use what's called the conjugate. And as you saw, the conjugate is the same binomial, but in this case we have a sum, so our conjugate will be a difference. If our binomial had a difference, our conjugate would be a sum. So we're going to multiply the bottom of this fraction by 1 minus root 3. Now, as we know from every fraction problem, if you multiply the denominator by something, you have to multiply the numerator by the same thing. So on the top of this, we have 8 times the quantity 1 minus root 3, and I'm going to leave it just like that for now. By the time this problem is over, we might have to do the distributive property, but for now I'm going to leave it like that until I find out what's happening with the denominator. In the denominator, we have a binomial times a binomial, and one way to multiply a binomial times a binomial is to FOIL. And pay special attention right now to what happens to the outer and inner terms when we FOIL. So the firsts are 1 and 1, so 1 times 1 is 1. Our outers are 1 times negative root 3, which is negative root 3. Our inners are positive root 3 times 1, which is positive root 3. And our lasts are positive root 3 times negative root 3, which is negative root 9. And as we know, if you multiply a radicand by itself, you get a perfect square radicand. So now we're going to simplify the bottom a little bit, and I'm just going to do this right here. We have 1, and then negative root 3 and positive root 3 add up to 0. That is why we are using the conjugate. It eliminates this part of the problem for us. And then the negative square root of 9 is negative 3. So now if we rewrite our problem, we have 8 times 1 minus root 3 in the numerator, and in the denominator now we have 1 minus 3, which is negative 2. So the reason that I left the top the way it was and I didn't do the distributive property is because of this step right now. I want to be able to simplify this because I know there's a greatest common factor that goes into 8 and negative 2 evenly, and that greatest common factor is negative 2. So I'm going to divide the 8 by negative 2, which will give me negative 4. And I'm going to multiply negative 2 times negative 2, which will give me 1. So now my expression looks like this. I have negative 4 times 1 minus root 3 over 1. And since the denominator is 1, I'm not even going to write it. Now that I have this part finished, in order to finish the problem and put it in its simplest form, I'm going to eliminate the parentheses by doing the distributive property. So my final answer will be negative 4 times 1 is negative 4, and negative 4 times negative root 3 is positive 4 root 3. And that expression is the simplified version of our original fraction. In our second example, we have the square root of 13 over root 5 minus 2, And again, this is not in its simplest form because the denominator has a radical in it. So we need to get rid of that by rationalizing. But since the denominator is a binomial, again, we're going to rationalize by using the conjugate. Now, this is a difference, so our conjugate will be a sum. And with every fraction problem, if you're going to multiply the bottom by something, you have to multiply the top by the same thing. So we're going to multiply root 13 times root 5 plus 2, and we're going to multiply the quantity root 5 minus 2 times the quantity root 5 plus 2. So just like I did on the last problem, I'm going to hold off on the top just in case it's easier in the end. I probably will still do the distributive property, but I don't want to have to redo a part of the problem that I've already worked before. All right, so on the bottom, again, we are going to FOIL. So our firsts are root 5 and root 5, which is root 25. Our outers are root 5 and 2, which is plus 2 root 5. Our inners are negative 2 and root 5, so that's negative 2 root 5. And our lasts are negative 2 and positive 2, which is negative 4. So every time you have a sum and difference pattern, the outer and the inner are going to drop out because they add up to 0, right? So then our first, it's a radicand times itself, so we get a perfect square radicand. So the actual value of the square root of 25 can be expressed without using a radical sign. That's just 5. Those make 0, and that's negative 4. So 5 minus 4 is 1. So when I rewrite my problem, the denominator now, after we've rationalized it by using the conjugate, is only a 1. So I'll have the square root of 13 times the square root of 5 plus 2 over 1. So I'm not even going to write the 1, but now I am going to have to do the distributive property. So root 13 times root 5 is root 65, and root 13 times 2 is 2 root 13. And so this has radicals in it, but they're not in the denominator. So this is a simplified version of our original fraction. All right, in our final example, we can see that this expression is not in its simplest form because we have not one, but 2 radicals in the denominator. So I'm going to start off, and to rationalize this, I'm going to have to use the conjugate, and this is a sum, so my conjugate will be a difference. And if I multiply the bottom by the conjugate, I have to multiply the top by the conjugate as well. And just like in the other problems, I'm going to hold off on the distributive property. So I have 12 times the quantity root 2 minus root 7. And then in the denominator, just like in the other problems, we're going to FOIL. And when I multiply my first, I have a radicand times itself. So that's going to give me a perfect square. So that's going to be the square root of 4. For my outers, I have root 2 times negative root 7, which is negative root 14. And for my inners, I have positive root 7 times positive root 2, which is positive root 14. And just like on all the other problems, our outer and inner is going to drop out. They're going to add up to 0. And then here we have a radicand times itself. That's going to give us a perfect square. So that's going to be minus root 49. So now in that denominator, I'm going to go ahead and simplify it right now. This is a perfect square, so I can rewrite it without the radical sign and still represent its exact value, which is 2. These add up to 0, and here I can write it without its radical sign and represent its exact value, which is 7. So when I go to rewrite my problem, the denominator is going to be negative 5. So I have 12 times the quantity root 2 minus root 7 over negative 5. Now, I can't do any reducing right now because 12 and 5 don't have a greatest common factor. So I'm just going to keep going, and I'm going to do the distributive property. And so I have 12 times root 2, which is 12 root 2, minus 12 times root 7, which is 12 root 7, over negative 5. Now, one thing about this problem, whenever you have a denominator that comes out negative, usually that's not considered to be in its simplest form. So what we're going to do is we're going to write it just like this, but instead of writing the negative on the bottom in front of the 5, we're going to write the negative out in front of the whole entire fraction. So that's going to look like this. And now we have radicals, but they're not in the denominator, so this is the simplified version of our original fraction.